The night opens not with silence, but with a slow intake of breath, a hush across the universe that feels like anticipation. Out there, among the stars, there are places where the rules falter, where physics, our greatest achievement in making sense of existence, seems to bow its head in defeat. These places are not marked with signs, nor do they give warning. They are invisible until their influence makes itself felt, a strange gravity bending light like glass under heat. They are the mouths of night, black holes. A black hole is not merely an object, but a question that refuses to close. It is the most perfect prediction of Einstein's mathematics, and yet the most vicious wound in them. It is the place where space-time does not simply curve, but caves in upon itself, collapsing into an abyss so absolute that nothing, not even light the messenger of the cosmos, can outrun its hunger. But the deeper mystery is not the darkness itself, it is the silence behind it. When something falls in, is it gone forever? Or does reality keep its secrets somewhere beyond reach? Black holes are engines of paradox. They are born from death, the death of massive stars, yet in dying, they create something stranger than life. They destroy information, yet might hold the key to the fundamental code of the universe. They obey Einstein's relativity with merciless precision, and yet, at their heart, they summon infinities that the equations themselves cannot tolerate. Imagine a map with no border, a page that folds itself until it is only a single point. Imagine time slowing, stretching, dissolving as you drift closer to an invisible horizon, and then gone. Beyond lies a region no traveler can report back from, no signal can escape, no truth can be verified. This is where our story begins, in the contradiction at the core of modern science. Do black holes confirm the completeness of physics, or do they break it? The first shadows of this mystery were not discovered in the deep lensing power of modern telescopes, but in the fragile ideas of thinkers who lived long before the word physics had hardened into its modern form. In the late 18th century, two minds, John Michell, an English natural philosopher, and Pierre-Simon Laplace, the French mathematician and astronomer, proposed something that, at the time, seemed more speculation than science. What if a star were so massive, so compact, that even light could not escape its surface? Mitchell called them dark stars. He reasoned that gravity, if strong enough, would bend not only the paths of stones and comets, but also the paths of light. With Newton's conception of light as particles, it seemed plausible. If the escape velocity exceeded the speed of light, then those beams would be forever trapped. No light could reach the eyes of a distant observer. The star would appear invisible. Laplace arrived at the same conclusion independently, writing in the 1790 seconds that such bodies may really exist in nature. But in their time, these musings were curiosities, footnotes in the margins of natural philosophy, with no data to anchor them. A century later, in 1915, Albert Einstein published his general theory of relativity. With it came the possibility of describing space and time not as rigid scaffolding, but as a dynamic fabric, warping under the influence of mass and energy. Within weeks of its publication, a German soldier on the Eastern Front, Karl Schwarzschild, solved Einstein's equations for the case of a spherical, non-rotating mass. His solution was elegant, exact, and terrifying. It suggested that space-time itself contained a radius, a boundary, beyond which all paths led inward, a place where escape, even for light, was impossible. For decades this was treated with suspicion. Was the Schwarzschild radius a real feature of the universe, or a mathematical artifact? Einstein himself doubted such objects could form in reality. Yet with each new generation of scientists, the suspicion deepened into something harder to dismiss. the dark stars of Mitchell and Laplace, had returned not as curiosities, but as a physical inevitability of relativity itself. The early hints were whispers, shadows at the edge of imagination, but they carried the seeds of a question that would not let go. What happens when gravity wins completely? The inevitability of collapse emerged not from poetry or speculation, but from the iron logic of equations written in the aftermath of war. By the late 1932, the stars themselves were becoming laboratories for extreme physics. Astronomers had begun to classify their deaths: white dwarfs, compact corpses of sun-like stars, neutron stars, the astonishingly dense remnants of more massive suns. Yet a question lingered: what of stars heavier still? Was there a limit beyond which matter could no longer resist its own gravity? In 1939, J. Robert Oppenheimer, together with his student Hartland Snyder, published a paper that would set the course of this mystery forever. They described the collapse of a massive star, one so heavy that not even neutron degeneracy pressure, the desperate quantum pushback of neutrons themselves, could halt its implosion. Their equations showed a catastrophic inward fall, a shrinking without end. For a distant observer, the collapse would appear to slow as the surface of the star approached the Schwarzschild radius, light climbing out with more and more difficulty, signals stretching into redder and redder wavelengths. To that observer, time itself seemed to freeze at the horizon. Yet for the star's own matter, for the particles rushing inward, the collapse was swift, unstoppable, and absolute. Here was no dark star conjured by Newtonian mechanics, but a direct, ruthless consequence of relativity. Gravity was not simply strong, it was victorious. Once the mass of a dying star crossed that invisible threshold, nothing could stop the implosion. The result was a region cut off from the rest of spacetime, its center a singularity where the mathematics collapsed into infinities. The paper was largely ignored at the time. The world was marching toward war, and Oppenheimer's own destiny was bending toward nuclear weapons. But the logic could not be undone. Stars, the very forges of elements, had fates stranger than death. For those above a critical mass, collapse was not only possible, it was inevitable. The universe itself contained traps from which no light, no time, no story could escape. The silence that followed Oppenheimer and Snyder's insight was not a dismissal, but a pause before realization. Physics had uncovered not only a new kind of object, but a new frontier, one that would test every rule it had ever written. The horizon is not a wall, not a surface you could touch, yet it is the most consequential boundary the universe has ever drawn. The event horizon of a black hole is not made of matter. It is geometry itself, a line in space-time that divides the possible from the impossible. To those who linger far away, the horizon is an optical trick. A star collapsing toward it appears to slow, its light stretched redder and dimmer until the glow seems to freeze. The star does not vanish all at once, but rather fades asymptotically, as though eternity itself were required for it to complete the fall. To the infalling matter, however, no delay is felt. The plunge continues in proper time, quick and unrelenting, as the surface crosses the horizon without drama. No flare, no rupture, no shout, only the smooth continuation of a doomed trajectory. In this contradiction lies the strangeness. Relativity teaches that both descriptions are true. For the distant observer, the horizon is a curtain time itself has stitched. For the falling traveler, it is nothing more than another point along the path, indistinguishable until the singularity waits ahead. The event horizon is not a substance, but an agreement written into spacetime's laws, a frontier that nothing within can send signals across. Philosophically, it is a threshold of knowledge. The cosmos beyond is cut off, hidden in perfect silence. Every law of science depends upon observation, and here is a place where observation ends. What lies past the horizon? A singularity of infinite curvature, say the equations, but no measurement can confirm it. All the information about the star, its structure, even the details of what fell in, seems erased from the outside view, compressed into a smooth, black geometry. It is as though the universe itself conspires to withhold secrets, erecting an edge where stories terminate. The horizon is the stage curtain of the cosmos, forever drawn, yet hiding a performance that no one in the audience can ever watch. At the center of this structure, past the horizon where no signal returns, lies the singularity, a word that sounds mathematical, clinical, but which hides an eruption of meaning. In the equations of general relativity, the singularity is the point where curvature grows without bound, where density becomes infinite, where the fabric of space-time itself tears beyond recognition. What does it mean for something to be infinite in a physical world? Here, general relativity falters. The theory that has so elegantly described planets and stars, the bending of light, and the expansion of the cosmos, suddenly cries out in contradiction. It delivers a prediction that cannot be observed, a number that cannot be reconciled. For science, it is like staring at a page where the text dissolves into illegible marks. The singularity is not a thing in space, it is the end of space. It is not a moment in time, it is the breakdown of time itself. If an observer could somehow cross the horizon and continue inward, they would find themselves on a trajectory that ends not in a place but in an inevitability, a collision with the failure of the very geometry that carried them. In classical relativity, all paths point to this collapse. No escape, no continuation. This is why black holes break more than stars. They break determinism. In physics, determinism is the belief that if we know the state of a system, we can calculate its future. The singularity denies this. The future cannot be calculated because the equations dissolve into nonsense. What lies beyond that point cannot be described by Einstein's framework. Stephen Hawking and Roger Penrose formalized this in the 1960 seconds with their singularity theorems. They proved that under very general conditions, singularities are not avoidable oddities, but inevitable consequences of gravitational collapse. They are not exceptions, they are the rule. And so, at the heart of every black hole lies a silent scream, a signal that the universe is both deeper and more fractured than the equations suggest. Singularities are not physical in the ordinary sense. They are physics waving a white flag. They are the boundaries where the map ends, where a new theory must begin. To picture a black hole is to attempt the impossible, to imagine not an object, but the structure of space-time itself under conditions so extreme that intuition falters. In the 1960 seconds, mathematicians and physicists began to draw maps of these regions, not with inked coastlines or mountains, but with the curves of light rays and the flow of causality. These were Penrose diagrams, tools that compress infinity into a finite sketch, distilling the essence of how space and time behave near the abyss. On these diagrams, lines of light are fixed at 45 degrees, slanting across the page like the beams of a celestial lantern. The trajectories of matter, slower than light, wind between them, sometimes trapped, sometimes free. In this language of tilted axes and compactified infinity, the truth of black holes revealed itself with ruthless clarity. Once a horizon is crossed, every future path converges inward. There is no choice, no detour, no hidden escape route. All timelines end at the singularity. Such causal cartography showed more than inevitability. It revealed symmetries and surprises. For the eternal black hole, an idealized solution not born of stars but existing forever, The Penrose diagram suggested other regions, mirror universes connected through the geometry, and wormhole-like bridges known as Einstein-Rosen bridges. These connections, ephemeral and untraversable, hinted at the possibility that space-time might be more interconnected than daily experience could ever reveal. Even in simpler forms, the diagrams displayed the Great Divide. Outside, observers linger in a universe where signals can still move freely. Inside, all arrows point toward collapse. Horizons are drawn not as physical barriers, but as boundaries in the very flow of cause and effect. To cross one is not to hit a wall, but to step across a threshold in the grammar of reality itself. These maps taught physicists to see black holes not as monstrous objects, but as arenas where the very logic of space-time must be reimagined. They showed that gravity does not merely bend space, it rewrites the rules of past and future, constrains what can be known, and rearranges what it means for one event to cause another. In this cartography of shadows, physics began to grasp that black holes are not merely in the universe, they are the universe reshaped, folded into geometries that mock human imagination, yet obey the stern precision of mathematics. If a black hole could ever be called simple, it is only in its first form, the static, silent sphere of Schwarzschild's imagination. But the universe does not deal in stillness. Stars spin, galaxies whirl. Collapse is rarely quiet. And so the equations of relativity were pressed further, twisted by mathematicians seeking solutions for rotating bodies. In 1963, Roy Kerr, a New Zealand mathematician, found one. His solution was breathtaking: the geometry of a rotating black hole, complete and exact, elegant in its complexity. No longer a mere spherical abyss, the rotating black hole became a churning vortex of space-time itself. In the Kerr solution, rotation drags the very fabric of the cosmos around it. This effect, frame dragging, means that no object, not even light, can remain still in the region close to the hole. The rotation forces everything into its spin, carrying space-time like a whirlpool dragging water into a spiral. Around the black hole lies the ergosphere, an oblate region where motion is compulsory, where particles are swept into rotation. Yet paradoxically, this region also offers a door. It allows energy to be extracted. The Penrose process, proposed by Roger Penrose in 1969, described how a particle entering the ergosphere could split, with one fragment swallowed by the hole and the other escaping, carrying away more energy than it arrived with. Here was a vision of black holes not just as devourers, but as engines, capable of giving as well as taking. Later, this idea would inspire explanations for the colossal jets of plasma that erupt from galactic cores, jets so powerful they outshine entire galaxies. The Kerr black hole is a richer and stranger creature than its static cousin. It possesses not just a horizon but two, an outer and an inner, separated by regions where predictability itself falters. Beyond lies the ring singularity, not a point but a loop where space-time contorts into forms alien to intuition. The mathematics allows, at least in theory, passage through such singularities into other universes or other times, though nature, through instabilities, likely bars the way. In this rotating darkness, simplicity gave way to a complexity that mirrored the restless universe itself. Black holes were no longer mute sinks of gravity, but dynamic, energetic, and perhaps even creative participants in the cosmic dance. Their rotation was not an accident, but a revelation that even the abyss has spin, and with it, possibilities. As the equations matured, another paradox emerged. If black holes are defined by their horizons, what distinguishes one from another? In the early 1970 seconds, physicists proposed the no-hair theorem, a stark principle, suggesting that black holes are profoundly simple objects. According to this view, once a star collapses into a black hole, all the intricate details of its birth, the composition of its matter, the turbulence of its plasma, the individuality of its history are erased. What remains is describable by only three numbers: mass, charge, and angular momentum. In this picture, a black hole has no hair. It carries no scars, no fingerprints, no memory of what it has consumed. Whether a star of hydrogen or helium, whether a planet, asteroid, or photon sea, everything ends in the same perfect geometry. Outside the horizon, all is smooth. The violent chaos of collapse is hidden behind an unyielding uniformity. And yet, science is uneasy with erasure. The laws of quantum mechanics insist that information cannot simply vanish. If black holes are truly bald, the universe loses track of detail forever, and the great conservation laws of physics collapse along with the stars. This unease has seeded 1,000 debates, each seeking the loophole where reality might be keeping its books balanced. Some suggest that the horizon is not as smooth as it appears. Quantum corrections may endow it with subtle features, so-called soft hair, delicate patterns of field excitations clinging to the boundary, encoding faint echoes of what has fallen in. Others imagine that the black hole's interior is not empty but woven with microstructure, a dense tapestry of quantum states too fine for relativity to capture, yet rich enough to store the lost information. The simplicity of the no-hair theorem, once a triumph of elegance, now feels like a mask concealing a deeper complexity. If black holes truly reduce the universe to three numbers, they shatter the principles of quantum theory. If they do not, then hidden whispers, soft hair, entanglement patterns, holographic codes must exist, waiting to be uncovered. What began as a proclamation of baldness has become one of the most haunting questions in modern physics. Does the abyss forget, or does it remember in ways too subtle for us to yet understand? From the coldest silence, black holes began to whisper of heat. In the early 1970 seconds, Jacob Bekenstein, a young graduate student, dared to imagine that black holes might not be exempt from the second law of thermodynamics. The law, stern and universal, declares that entropy, the measure of disorder or information, must always increase. Yet if black holes truly swallowed everything without trace, they seem to defy this rule. Throw a book into a fire, and its information disperses into ash, smoke, and radiation. Throw a book into a black hole, and from the outside, all trace is gone. Entropy would appear to decrease. Bekenstein proposed a radical solution. Black holes themselves must possess entropy. Their entropy, he argued, was proportional not to their volume but to the area of their event horizons. The greater the surface of the horizon, the greater the hidden information it might conceal. It was an audacious idea, one that reshaped the way physicists thought about these objects. Stephen Hawking, skeptical at first, sought to disprove Bekenstein. But in the attempt, his calculations revealed something even stranger. In 1974, Hawking showed that black holes are not perfectly black. Quantum fluctuations near the horizon allow particle-antiparticle pairs to flicker into existence. Normally they annihilate, vanishing back into the vacuum. But at the edge of a black hole, one partner can be swallowed while the other escapes, carrying energy outward. To a distant observer, the black hole glows with a faint thermal radiation. This revelation shattered the old image of black holes as eternal prisons. If they radiate, then they evaporate. Slowly, unimaginably slowly for the giants in the cosmos, but with certainty. A black hole is not forever. It shrinks, it fades, it dies. The implications were seismic. Black holes now belong to the realm of thermodynamics and quantum theory. They had a temperature, a spectrum, a finite lifetime. They were not only gravitational monsters but also thermodynamic bodies, subject to the same laws that govern steam engines and stars. Yet this insight deepened the paradox. If a black hole can evaporate completely, what becomes of the information it swallowed? Does the radiation carry it away, coded in subtle patterns? Or does it vanish, breaking the fundamental promise of quantum mechanics? From the marriage of Bekenstein's entropy and Hawking's radiation was born one of the greatest scientific dilemmas of the modern age, the black hole information paradox, a puzzle that has yet to yield its final answer. The realization that black holes radiate transformed them into thermodynamic entities, and with this shift came a new elegance, the laws of black hole mechanics. In the early 1970s, Bardeen, Carter, and Hawking formalized these rules, framing them as the gravitational mirror of the familiar laws of thermodynamics. It was as though the abyss itself had been drafted into the same cosmic contract that governs engines, stars, and ice melting in a glass. The first law spoke of energy. It tied changes in a black hole's mass, angular momentum, and charge to changes in its surface area and surface gravity, echoing the way heat, work, and entropy interact in ordinary systems. The second law declared that the area of a black hole's event horizon could never decrease, an analog to the second law of thermodynamics, where entropy must always rise. This law suggested that horizons are one-way growths. They expand as matter falls in but never contract. The third law mirrored the impossibility of absolute zero. Just as no physical process can reduce a system's temperature to exactly zero, no finite sequence of steps can reduce a black hole's surface gravity to zero. Extremal black holes, those with maximum charge or spin, approach this limit but never quite arrive. And finally, the zeroth law established uniformity. The surface gravity of a stationary black hole is constant across its horizon, just as temperature is uniform throughout a system in thermal equilibrium. Together, these laws revealed black holes not as strange exceptions to the universe's bookkeeping, but as participants in its deepest rules. Their horizons were entropy, their surface gravity was temperature, their evaporation was heat loss. But with this recognition came unease. If horizons grow, if their area is tied to entropy, what happens as they radiate and shrink? Hawking's discovery showed that the second law of black hole mechanics had to be modified, the generalized second law, accounting for both black hole entropy and the entropy of radiation outside. Still, the balance was preserved. It was a breathtaking symmetry, a glimpse of unity between the geometry of space-time and the statistics of microscopic states. Yet it also sharpened the paradox. The laws seemed to insist that information was not lost, but the mechanics of radiation offered no clear mechanism for how it might be preserved. Here, on the event horizon's invisible surface, physics revealed its double nature: elegant, symmetrical, orderly, and at the same time precarious, incomplete, haunted by the possibility that the abyss might be breaking the very rules it seemed to honor. The paradox erupted from a calculation. Stephen Hawking, working in the mid-1970s, had discovered that black holes radiate, glowing faintly with a thermal spectrum. This revelation meant that black holes were not eternal prisons but objects with lifetimes, evaporating over inconceivably long timescales. Yet, if they could evaporate completely, a profound problem arose. Imagine tossing a book into a fire. Its words are gone, but the information is not destroyed. It is dispersed in the smoke, ash, and radiation. Quantum mechanics assures that this is always the case. Information can be scrambled, but never erased. But with a black hole, the story darkens. If matter falls in, and the black hole eventually evaporates away, what becomes of the information about that matter? Hawking argued that the radiation is purely thermal, carrying no trace of the structure of what was lost. When the black hole vanishes, all the information that entered it would be erased from the universe. This is not merely unsettling, it is catastrophic. The principle of unitarity, one of quantum theory's most sacred laws, would be broken. Physics, which relies on predictability, would be shattered at its foundation. This is the black hole information paradox. On one side stands relativity, with its event horizon and silent singularity. On the other side stands quantum mechanics, with its fierce insistence that information survives every transformation. Both theories are supremely successful in their domains, tested and confirmed in countless experiments. Yet together, at the edge of a black hole, they scream at one another in contradiction. The paradox is not trivial. It is a question about whether reality itself is knowable, whether the universe plays fair with its rules, or whether it permits erasure of history. If information can vanish, then the laws that govern atoms, stars, and time itself are incomplete. If information survives, then relativity's picture of the horizon is somehow flawed. Hawking himself leaned toward destruction. He proposed that black holes truly do erase information, that physics must accept this loss. But many others resisted. The paradox was too severe, too corrosive to the order of science. Something, somewhere, must be wrong in the picture. Thus began decades of argument, the most profound and heated debate in theoretical physics. Black holes, once thought of as the most simple and featureless objects in the universe, had become its greatest puzzles. The paradox raged through the halls of physics, igniting conferences, papers, and debates that stretched across decades. How could two theories, each so profoundly successful, demand mutually exclusive truths? Relativity insists that nothing escapes the event horizon. Quantum mechanics insists that information cannot be lost. The collision seemed irreconcilable. Yet, in the early 1990 seconds, a tentative peace was proposed, one born not from resolution but from perspective. It was called black hole complementarity. The idea was simple in phrasing but profound in implication. Perhaps no single observer can ever witness both sides of the contradiction. To an outside observer, information is never truly lost. Matter that falls toward the horizon appears to smear itself across the surface, encoded in the black hole's boundary, as though the horizon itself were a vast recording device. To the infalling traveler, however, nothing unusual occurs at the horizon. They pass through smoothly, carrying their information intact toward the singularity. Both pictures are valid, complementing one another without contradiction, because no observer can see both stories at once. The one who falls inward cannot report back. The one who remains outside never sees the passage completed. Nature, in this interpretation, is not lying, it is partitioning. Reality is observer-dependent, stitched together from frames of reference that never overlap. This truth satisfied some, for a time. It preserved the sanctity of relativity's horizons while also keeping the door open for quantum mechanics' conservation of information. Yet it came at a cost. Complementarity demands a strange kind of duality. The horizon is both a gentle crossing and a recording screen. It is both smooth and searing with hidden data. It is two realities layered upon one another, neither of which can be denied. Skeptics pointed out the fragility of this balance. Could nature really preserve consistency by hiding contradictions behind causal walls? Was complementarity a deep truth of space-time, or a clever patch to avoid admitting ignorance? For nearly 2 decades, this principle held sway, a truce born of necessity rather than clarity. It promised that black holes need not break physics outright, that perhaps the universe had built into its very architecture a way to avoid impossible paradoxes. But under the surface, questions festered. If horizons are smooth, how can they also hold the entire informational content of the cosmos that falls within? If information is not destroyed, how does it emerge again in Hawking radiation? The calm of complementarity was a pause, not a solution, a fragile peace awaiting the next disruption. And that disruption was coming, drawn in fire. The fragile truce of complementarity could not endure. In 2012, a shock tore through theoretical physics, shaking even those who had grown accustomed to paradox. A group of researchers, Almheri, Marolf, Polchinski, and Sully, whose initials gave rise to the acronym AMPS, posed a question that cracked open the horizon itself. If information is preserved, how can the horizon remain smooth? Their conclusion was unsettling. The horizon, they argued, cannot be both gentle and faithful to unitarity. If Hawking radiation carries information outward, then the interior and the radiation cannot remain entangled in the way complementarity demanded. Something must give. And what gave, in their calculation, was the equivalence principle, the very heart of Einstein's theory, which states that a freely falling observer should feel nothing unusual at the horizon. Instead, AMPS proposed, the horizon could be a furnace, a wall of searing energy, a firewall, meeting any infalling observer. Crossing into a black hole, then, would not be a smooth transition, but an annihilation at the very threshold. No gentle plunge, no quiet drift past the point of no return, only violent incineration. This was heresy. For nearly a century, relativity had insisted that nothing peculiar happens at the horizon. The drama lies within, not without. The firewall proposal shattered this, suggesting that the most sacred principle of relativity might fail precisely where the paradox was sharpest. The physics community erupted. Could Einstein's equivalence principle, tested and confirmed in countless experiments, break down at the edge of a black hole? Was the firewall a real feature of the cosmos, or a sign that something deeper was misunderstood? Some resisted, arguing that firewalls were too crude, too violent, too dismissive of the elegance of relativity. Others leaned toward them, reasoning that quantum mechanics' insistence on information preservation was too fundamental to abandon. Between them, the debate burned, echoing the very imagery the proposal conjured. The firewall controversy forced physicists to confront an uncomfortable truth. No existing theory could simultaneously honor relativity, quantum mechanics, and unitarity without contradiction. The horizon was no longer a smooth veil of mystery. It had become the front line of a battle between the deepest principles of nature. For those who gazed into this abyss, the question grew sharper, more unsettling. If the horizon is fire, then black holes are not simply strange, they are catastrophic for the very foundations of physics. If it is not fire, then some other hidden mechanism must exist, waiting in the darkness to be revealed. The flames of the firewall paradox lit the stage for an idea as audacious as it was mysterious. If the horizon could not be smooth, and if information could not be destroyed, perhaps the answer lay not in destroying principles, but in unifying them under a deeper vision. In 2013, Juan Maldacena and Leonard Susskind proposed a radical bridge, ER equals EPR. The name itself was a cipher. ER for Einstein, Rosen, the wormholes first imagined in the 1930 seconds as tunnels linking distant regions of spacetime. EPR for Einstein, Podolsky, and Rosen, whose famous 1935 paper had challenged the completeness of quantum mechanics by introducing the paradox of entanglement. Two acronyms, born from different puzzles, suddenly bound together. Perhaps wormholes and entanglement are the same thing, two faces of the same hidden structure. If true, this proposal rewrote the very notion of connection. Particles entangled across vast distances are not linked by invisible threads, but by wormholes, tiny, non-traversable bridges of space-time geometry. And if Hawking radiation is entangled with the black hole's interior, then perhaps those links are wormholes too, stretching across the horizon, weaving inside and outside into one tapestry. In this vision, the horizon is neither a firewall nor a smooth emptiness. It is a web of entanglement, geometry itself born from quantum ties. The black hole's information does not vanish, it is stored and transmitted through these connections, encrypted into the very fabric of space-time. Philosophically, ER equals EPR is a whisper of unification. It suggests that gravity, the bending of space-time, and quantum entanglement, the binding of particles, may not be separate languages but dialects of the same deep grammar. Space-time itself might emerge from the quantum dance of entangled states, wormholes blossoming from invisible correlations. Skeptics remain, pointing out that ER equals EPR is not a proven law but a bold conjecture. Yet it has opened a new horizon of thought. Instead of choosing between relativity and quantum mechanics, the idea offers a path where both are preserved, fused by entanglement into geometry. It is a picture at once breathtaking and humbling, that every black hole, every horizon, may be threaded with unseen bridges, wormholes that are not roads to elsewhere, but the very scaffolding of reality itself. Where physics once saw contradiction, it may be looking at unity, veiled in symbols waiting to be deciphered. The horizon, once imagined as a silent curtain, now appeared as a screen. From this idea emerged one of the most transformative principles in modern physics, the holographic principle. It began with Gerard Hooft and was expanded by Leonard Susskind in the 1990 seconds, born from the tension between black hole entropy and quantum theory. If the entropy of a black hole is proportional to its surface area rather than its volume, then perhaps the universe itself is encoded not in the depths of 3 dimensions, but on the boundaries that contain them. The principle suggests that all the information within a black hole, the full complexity of every particle and every field that has ever crossed its horizon, can be described by degrees of freedom painted across its 2-dimensional surface. The horizon is not just a veil, it is a ledger, a canvas on which the universe writes the details of its story. This radical idea overturns intuition. Reality may be a projection, like a hologram, with the truest description residing on a boundary rather than in the space it encloses. Juan Maldacina's work in 1997 gave this vision mathematical flesh through the ads divided by CFT correspondence. He showed that a certain kind of gravitational theory in a higher dimensional bulk space-time could be exactly equivalent to a quantum field theory without gravity on its lower dimensional boundary. In this correspondence, space-time and gravity emerge from quantum information, woven into geometry by entanglement. Black holes in the bulk correspond to hot thermal states in the boundary theory, their entropy and evaporation mirrored in precise, calculable ways. Suddenly, black holes were no longer solitary enigmas, but test cases for the deepest unity between gravity and quantum theory. Their horizons became canvases, their singularities shadows of more complete descriptions. The holographic principle promised that what relativity and quantum mechanics could not reconcile separately, they might harmonize when seen as 2 perspectives of the same encoded story. Philosophically, the implications are staggering. If the holographic principle is true not only for exotic ad spaces but for our own universe, then the cosmos itself may be a projection, the 3-dimensional tapestry of stars and galaxies emerging from information inscribed on a cosmic boundary. Black holes, then, are not exceptions, they are windows, reminding us that what we perceive as depth may, at its heart, be information spread across a surface. The abyss does not erase, it records, and in those silent records, Physics glimpses not the end of law but the beginning of a new order, where space, time, and reality itself are woven from information. Entropy had given black holes a hidden richness. If their horizons encode information, then the natural next question followed: what are the microscopic bits that make up this entropy? For ordinary matter, entropy is understood as the counting of microscopic states, the ways atoms and molecules can arrange themselves. For black holes, whose entropy is measured in horizon area, the puzzle became one of the most urgent in modern physics. What are the microstates of a black hole? In the mid-1990s, string theory offered an answer. Andrew Strominger and Kumran Waffer studied certain supersymmetric black holes, exotic cousins protected by symmetry that could be tamed by calculation. To their astonishment, when they counted the number of ways strings and branes could form such an object, the result matched precisely the Bekenstein-Hawking entropy formula. The area of the horizon was not a mystery anymore. It was the shadow of countless quantum configurations, microstates encoded in the fabric of string theory. This breakthrough electrified physics. For the first time, a black hole's entropy could be traced to a microscopic accounting, not a macroscopic analogy. Yet it was limited. The result applied only to special, idealized black holes, supersymmetric, extremal, unlike the ones birthed by collapsing stars in our universe. Still, it opened a door, suggesting that in some deep theory, black holes are not bald at all. Their horizons conceal a multitude of quantum states, a hidden orchestra whose music is too subtle for classical relativity to hear. Other approaches joined the search. Loop quantum gravity proposed that space-time itself is quantized, made of discrete loops of geometry, and that black hole horizons are punctured by these loops, each carrying a quantum of area. In this picture, entropy is counted by the number of ways these punctures can arrange themselves. The horizon becomes a mosaic of Planck-scale facets, a granular record of information. Speculative models multiplied, fuzzball proposals suggesting that every microstate corresponds to a horizonless configuration of strings, with the traditional black hole emerging only as an average. Quantum gravity hinted that singularities dissolve into a sea of microstructure, with the horizon not an eraser but a veil drawn over intricate detail. Though no final answer is agreed upon, the direction is clear. The entropy of black holes points toward a new layer of physics, one where geometry emerges from microstates, and the smoothness of horizons is a statistical illusion. The counting of microstates is not a mere exercise, it is a glimpse into the quantum granularity of spacetime itself. In this vision, black holes are not the end of law, but the proof that beneath the apparent simplicity of the cosmos lies a complexity beyond imagination, a hidden multitude encoded in the very skin of darkness. If entropy hints that black holes encode their secrets in countless hidden states, then the natural question follows: how does that information return, if at all, in the process of evaporation? For years, Hawking's calculation painted the radiation as purely thermal, carrying no imprint of what had fallen in. But quantum mechanics, unyielding in its demand for unitarity, suggested otherwise. Somewhere in the faint stream of particles escaping the abyss, the story of the infallen world must be hidden. This puzzle is often traced through the metaphor of scrambling. A black hole, physicists argue, is the universe's fastest scrambler of information. Anything that enters is torn apart, its data dispersed among the microscopic degrees of freedom on the horizon in ways that defy decoding. Yet, in principle, the information is not destroyed, only scrambled beyond recognition. Like ink spilled into water, the original pattern dissolves, but the molecules remain, hidden in the turbulence. Don Page, in the 1990 seconds, calculated how information should emerge if black holes obey quantum unitarity. The result was the now famous Page curve. At first, radiation looks thermal, devoid of detail, but after roughly half the black hole's lifetime, information must begin to trickle out, encoded in subtle correlations. At the end of evaporation, if unitarity holds, all information is restored. Recent advances have made this picture sharper. In 2019 and 2020, researchers used the tools of holography and quantum gravity to calculate radiation entropy more carefully. Their work revealed the presence of islands regions inside the black hole that must be included in the quantum bookkeeping of radiation. These islands allowed the page curve to emerge naturally, preserving unitarity without violating known laws. It was the first glimmer of a solution that reconciled Hawking's radiation with the demands of quantum mechanics. Still, the mechanism remains mysterious. How exactly is the information encoded in the radiation? What precise role does entanglement play? Some invoke the idea of quantum teleportation across the horizon. Others suggest the encoding is so chaotic that only in principle, not in practice, could it ever be decoded. What matters is the implication. Black holes may not be destroyers of information after all. They are cosmic processors, scrambling, delaying, and eventually releasing the data of what they consume. The paradox, once thought insurmountable, has begun to bend toward resolution, not through firewalls or destruction, but through the subtleties of entanglement and the persistence of quantum law. And yet, even as the page curve reassures us that physics may not break, it whispers something deeper, that information is not simply preserved, but transformed. In the furnace of a black hole, the universe reveals its dual nature as both memory and metamorphosis. The paradoxes of information, scrambling, and entropy live in theory, but in the past decade, black holes have stepped out of equations and into the data streams of instruments more sensitive than any before. In 2015, a faint tremor passed through Earth. It was not sound nor light, but a ripple in the very geometry of spacetime, the first detection of gravitational waves by LIGO. The signal was the death cry of two black holes spiraling into one another, merging into a single, larger abyss. For a brief instant, the collision released more energy than all the stars in the observable universe combined, yet in the form of gravitational waves, silent undulations of spacetime. As the waves rang outward, they carried the unmistakable fingerprint of the new black hole settling into equilibrium. These were the ringdowns, echoes of vibration as the merged object adjusted into its final form. General relativity makes a clear prediction. The ringing of a black hole should depend only on its mass and spin, not on the details of its past. This is the no-hair theorem in action, tested on a cosmic stage. And indeed, the signals matched Einstein's expectations with stunning precision. The black holes sang in tones predicted decades earlier, confirming once again the extraordinary accuracy of relativity in the strong gravity regime. But scientists listen for more than confirmation. They hunt for deviations, for subtle echoes in the data that might betray hair where none should exist, or quantum corrections etched into the horizon. Some claim to have glimpsed hints, anomalous echoes, in the ring-down waves that could signal departures from pure general relativity. These claims remain tentative, contested, fragile in their statistical weight. Yet the very possibility stirs excitement. Gravitational wave astronomy is still young. As detectors grow more sensitive, LIGO, Virgo, KAGRA, and the future space-based LISA, the catalogue of mergers will expand, offering a new library of tests. Each collision is a chance to probe whether black holes are truly the simple, bald objects relativity describes, or whether quantum structure seeps into their song. The beauty of these observations lies not only in their confirmation, but in their potential for betrayal. If a single ringdown fails to align with relativity's predictions, it would be a crack in the edifice, an opening into new physics. Black holes, once invisible, are now singers in the cosmic choir, and physicists strain to hear whether their voices conceal harmonies beyond Einstein's score. For the first time, the question of whether black holes break physics is not confined to blackboards. It vibrates in the fabric of space-time itself, measured in detectors on Earth, awaiting the discordant note that may reveal the truth. For centuries, black holes were invisible, mathematical phantoms whose existence was inferred, never seen. But in April 2019, humanity was offered its first portrait of the unseeable. The Event Horizon Telescope, a planet-spanning array of radio observatories linked with atomic precision, revealed the shadow of the supermassive black hole in the galaxy M87. It was not a photograph in the ordinary sense, but a reconstruction of radio waves bent and delayed by gravity itself. The image showed a luminous ring, asymmetrical, glowing like a halo around a void. This was light from hot plasma, spiraling at near-light speed, warped by gravity into a circle of fire. At the center lay the darkness, the silhouette of the event horizon, a shadow carved not by matter but by the absence of escape. The size of the ring matched the predictions of general relativity with exquisite accuracy. A theory born on paper in 1915 had, a century later, been painted across the sky. Yet, the image carried more than confirmation. Polarization studies soon followed, tracing the alignment of light waves around the black hole. These patterns revealed magnetic fields twisting in arcs, guiding plasma and shaping the colossal jets that erupt from galactic cores. Suddenly, black holes were not abstract entities but dynamic engines, their surroundings ablaze with forces too powerful to replicate on Earth. The portraits are growing sharper. In 2022, the Event Horizon Telescope unveiled the shadow of Sagittarius A*, the black hole at the heart of our own Milky Way. Smaller, more turbulent, its image flickers with variability, challenging astronomers to disentangle motion on timescales of minutes rather than days. Each new observation refines our understanding of how light dances near the horizon, testing relativity under conditions no laboratory could create. But these images also raise new questions. Do the brightness patterns conceal hints of quantum corrections to the horizon? Are the asymmetries mere turbulence or whispers of new physics? The ring is not a smooth, perfect circle. It flickers, warps, and blurs. Behind those deviations may lie either mundane astrophysics or the first signs of cracks in Einstein's description. What matters is the transformation. Black holes, once metaphors of invisibility, now cast their shadows upon our instruments. They have faces, shapes, and behaviors that can be watched, measured, tested. The boundary between theory and observation has thinned. We are no longer speaking only in mathematics. We are staring into the eyes of the abyss itself. And in those eyes, glowing at the edge of silence, the question lingers: do these shadows confirm that physics holds steady, or do they whisper that its laws are fraying at the edges of darkness? If the horizon is silence, the space just outside it is fury. Black holes are not isolated. Quiet spheres drifting in the void, they are surrounded by matter, drawn inward, compressed, and ignited into luminous violence. The disks that form around them, called accretion disks, are among the brightest objects in the universe, paradoxical companions to the deepest darkness. Matter spirals inward under gravity, colliding with itself, heating to millions of degrees. Friction and turbulence churn the gas into incandescent plasma, radiating across the electromagnetic spectrum from X-rays to radio waves. What we see as brilliant emissions are the last screams of matter before it surrenders to the horizon. Magnetism amplifies the chaos. Magnetic fields, twisted and stretched by the swirling plasma, can choke the flow of matter, piling it up until it resists further collapse. This leads to the phenomenon of magnetically arrested disks, where the accretion process is slowed, yet energy is stored in magnetic knots. When released, these fields can channel vast amounts of power outward, collimating plasma into narrow, relativistic jets. These jets are among the most extraordinary structures in the cosmos. They launch from near the black hole, piercing galactic cores, extending for thousands of light years. They carry energy and matter at near light speeds, sculpting the galaxies that host them, heating interstellar gas, and regulating star formation. Though the exact mechanism remains debated, simulations of general relativistic magnetohydrodynamics, GRMHD, have revealed how the rotational energy of the black hole itself can be tapped, funneled by magnetic fields into coherent streams of power. Such processes transform black holes from passive graves into engines. They consume, yes, but they also create, driving dynamics on galactic scales. Quasars, the blazing beacons of the early universe, owe their light to this interplay of gravity, magnetism, and plasma. Observations deepen the picture. X-ray telescopes detect the flicker of matter orbiting close to the innermost stable circular orbit, its timing probing the geometry of spacetime itself. Polarization studies trace magnetic alignments, mapping invisible fields at the edge of the abyss. Simulations match these signals, revealing how turbulence, pressure, and relativity entwine. In these luminous disks and furious jets, the black hole paradox grows sharper. Here, at the very edge of horizons, physics is tested under extremes of density, energy, and gravity. Do these behaviors confirm relativity or betray hidden corrections? Each photon, each flicker, carries the possibility of a crack in the theory. And yet, even as they challenge, they awe. Black holes, once imagined as silent voids, reveal themselves as orchestras of violence and structure-absorbing matter, but also reshaping galaxies, seeding new stars, and binding the cosmos in ways that extend far beyond their invisible borders. But not all encounters with black holes are the slow spirals of accretion disks. Sometimes, the meeting is sudden, violent, and terminal. A star, wandering too close to the invisible well, can find itself torn apart in a phenomenon known as a tidal disruption event. Gravity is not uniform across an extended body. For a star near a black hole, the pull on its near side is stronger than on its far side. Ordinarily, stars withstand such forces, bound by their own self-gravity. But when the difference becomes extreme, when the black hole's tidal forces exceed the star's binding strength, the star is ripped apart. Its gas stretches into streams, filaments unraveling like silk under invisible hands. To distant observers, this is not hidden in silence. The star's shredded material forms a luminous arc, some flung outward into interstellar space, the rest spiraling inward to form a temporary accretion disk. As it falls, the gas heats, emitting intense bursts of ultraviolet and X-ray light. For weeks or months, the black hole flares, suddenly revealed by its feast. These events are rare, perhaps one every 10,000 years per galaxy, but their brilliance allows them to be seen across cosmic distances. They are natural laboratories, exposing dormant black holes that otherwise lurk unseen at galactic centers. Each flare maps the physics of strong gravity, giving astronomers a fleeting but powerful glimpse of horizons at work. Observations have grown more precise. Telescopes like Swift and XMM Newton have captured light curves, spectral shifts, and the evolving glow of tidal disruption events. They confirm the predictions of relativity, the redshifting of matter as it spirals inward, the timing of debris falling back toward the horizon, yet they also raise questions. In some cases, the emission is jetted, as if the black hole channels the stellar debris into narrow beams, challenging models of how energy is distributed. Tidal disruption events remind us of the black hole's dual role, silent most of the time, yet capable of sudden revelation. They demonstrate the immense destructive power of horizons, yet also their utility as cosmic beacons. For a brief period, a star's death becomes a flare of knowledge, a transient light guiding our attempts to understand what happens when gravity triumphs utterly. And beyond the data lies the imagery. Stars, those luminous symbols of permanence, are not safe. They can be undone in hours, stretched, devoured, erased. The universe, in its vast theatre, stages dramas of loss and revelation, with black holes as the silent actors at their center. If black holes are born from the deaths of massive stars, then their growth should be measured in patient accretion disks, feeding them over millions of years, mergers adding mass step by step. Yet when astronomers look into the deep past, into the infant universe only a few 100 million years after the Big Bang, they find giants already in place. Quasars, blazing with the light of matter falling into supermassive black holes, have been observed at redshifts greater than 7, meaning they existed when the universe was less than 1 billion years old. Some harbor black holes with masses exceeding 1 billion suns. Their presence is a riddle. How could such enormity emerge so quickly when the cosmos itself was still young, its galaxies barely formed? Conventional models struggle. A stellar mass black hole, born from the collapse of the first stars, could in principle grow into a supermassive one, but only if it fed nearly constantly at the maximum possible rate, the Eddington limit, without interruption for hundreds of millions of years. Turbulence, feedback, and the chaotic nature of early galaxies make such perfect feeding unlikely. This tension has inspired alternative scenarios. Perhaps the seeds of these giants were not ordinary black holes at all, but direct collapse black holes, formed when enormous clouds of primordial gas collapsed directly under their own weight, bypassing the stage of star formation. These would begin not at a few solar masses, but at tens or hundreds of thousands, giving them a head start on cosmic timescales. Others imagine exotic processes, mergers of dense stellar clusters, runaway growth of primordial black holes, or even hints of new physics in the earliest moments of cosmic history. The existence of early supermassive black holes may be a fingerprint of conditions we do not yet understand, a sign that the infant universe was stranger and more fertile than our models allow. Observations continue to press the puzzle. Telescopes like the James Webb Space Telescope are peering deeper into cosmic dawn, searching for the faint light of galaxies feeding these early behemoths. Their data may decide whether growth alone explains the giants, or whether new seeds must be invoked. What is clear is that black holes, far from being passive endpoints, were active participants in shaping the earliest galaxies. Their jets and radiation may have sculpted the distribution of matter, influenced star formation, and helped weave the large-scale structure of the universe. They were not latecomers, but architects present from the beginning. In these ancient shadows, we find not only a mystery of growth, but a reminder. Black holes are not only destroyers of stars, they are among the first builders, shaping galaxies before the cosmos had even settled into maturity. While the supermassive black holes of galaxies dominate the modern universe, theorists have long wondered if smaller, more ancient cousins might also exist. Black holes not born from stars but from the very birth of the cosmos itself. These are primordial black holes, hypothetical relics of the Big Bang, forged in the seething chaos of the universe's first fractions of a second. In those earliest instants, the cosmos was a storm of quantum fluctuations, regions of slightly higher density flickering against a backdrop of expanding plasma. Normally, such fluctuations smoothed out as the universe stretched. But if some patches were dense enough, they might have collapsed under their own gravity, forming black holes directly tiny at first. perhaps no more massive than mountains or planets, but impossibly dense, their horizons enclosing the fury of the newborn universe. The idea has tantalizing implications. These black holes, scattered like seeds across space, could account for some or all of the dark matter, the invisible mass that outweighs normal matter by a factor of 5, yet betrays itself only through gravity. Unlike exotic particles or undiscovered fields, primordial black holes are made of nothing but gravity itself, no new physics required, only the ruthless application of Einstein's equations at the dawn of time. Astronomers have searched for them, hunting through microlensing surveys where a compact object passing in front of a star bends its light, betraying its presence. Some ranges of mass have been ruled out, others remain possible. LIGO's detections of black hole mergers revived interest. Some of the colliding objects appeared heavier than expected for stellar remnants, sparking speculation that they might be primordial, yet other explanations remain equally plausible. If they exist, primordial black holes may fill roles both subtle and profound. They could seed the growth of supermassive black holes, provide clues to inflationary physics, or even leave imprints in the background radiation of the universe. Some theories propose that the smallest among them may already have evaporated via Hawking radiation, perhaps leaving faint bursts of gamma rays or relic particles. Still, the evidence remains elusive. Each observation tightens the bounds, but the door is not closed. Primordial black holes hover at the edge of science, possible, tantalizing, unconfirmed. They are reminders that black holes are not only the product of stars and galaxies, but perhaps of the universe itself, born in the same fiery instant as time and space. In contemplating them, we confront the possibility that darkness is older than light, that the first structures of the cosmos were not stars, not galaxies, but silent holes, waiting patiently while the rest of creation unfolded around them. Not every abyss in theory must be a black hole. As the paradoxes deepened and the horizons seemed to challenge the very rules of physics, some scientists began to imagine alternatives, objects that mimic the gravitational pull of black holes, but avoid their most troubling features. These are the black hole mimickers, candidates like boson stars, gravastars, and fuzzballs, speculative constructs that ask whether the cosmos has been deceiving us with illusions. A boson star is one such candidate, built not of ordinary matter, but of hypothetical bosonic particles, fields that could clump together without collapsing into a singularity. Transparent and strange, they would bend light, almost like black holes but lack horizons. If boson stars exist, they would glow faintly rather than disappear, storing information without erasing it. A more radical vision is the gravastar, short for gravitational vacuum star. Proposed as an alternative to collapse, it replaces the singularity with a core of exotic vacuum energy. Instead of an event horizon, a thin shell of matter surrounds the interior, holding back collapse and preventing the formation of a true black hole. From afar, it would resemble a black hole closely, but in principle, no information is destroyed, only stored behind an unconventional wall of spacetime. String theory offers the most daring alternative, the fuzzball. According to this proposal, a black hole is not an empty cavity cloaked by a horizon, but a tangled web of strings and brains, a fuzzy ball of quantum states that extend outward. There is no singularity hidden behind a horizon. Instead, the entire region is saturated with structure. To an outside observer, a fuzzball appears indistinguishable from a black hole, but information is preserved in its quantum hair, never lost to an unreachable abyss. Each of these proposals is motivated by the desire to reconcile relativity with quantum mechanics, to preserve unitarity while escaping the tyranny of singularities. And yet, the evidence remains indirect. Observations of gravitational waves and black hole shadows so far align with relativity's predictions. But the precision of our instruments is still young, and subtle differences might yet be uncovered, echoes in the ringdown of mergers, slight deviations in horizon geometry, or unexpected signals in the distribution of cosmic radiation. Whether these mimickers exist or not, their importance is philosophical as much as physical. They remind us that what we call black holes may not be final truths, but working approximations, placeholders for a deeper structure that our theories are still struggling to name. They are thought experiments made flesh in mathematics, challenging us to test nature and ask, are we certain the darkness we see is truly the void we imagine? Perhaps one day, a deviation in the data will reveal that horizons are illusions, that singularities never form, and that what we thought were engines of paradox are instead guardians of hidden structure. Or perhaps not, and the black holes will remain exactly as Einstein described. Either way, the mimickers have expanded the imagination of science, daring it to question the certainty of its most elegant monsters. To question whether black holes are truly what relativity predicts is to place Einstein's great edifice itself on trial. General relativity has passed every test thrown at it, from the precession of Mercury's orbit to the bending of starlight during eclipses, from gravitational time dilation to the ripples of space-time captured by LIGO. Yet black holes push the theory to its breaking point. Singularities, firewalls, and paradoxes suggest that the theory, though powerful, is incomplete. Modified theories of gravity attempt to soften these fractures. Some propose changes at extreme densities, altering Einstein's equations so that collapse halts before singularities can form. Others invoke quantum corrections, stitching new terms into the curvature of space-time to tame infinities. These adjustments often aim to preserve the successes of relativity on large scales while rewriting its grammar near horizons. Among these approaches are extensions like F-R gravity, which modifies the relationship between curvature and matter, or scalar tensor theories, where new fields interact with space-time geometry. Other proposals come from the frontiers of quantum gravity, string theory, with its higher dimensions and vibrating strings, or loop quantum gravity, which replaces the continuum with discrete quanta of spacetime. In each case, the goal is the same: to prevent the absolute breakdown of law at the singularity. Observations act as judge and jury. Gravitational wave astronomy has begun to test whether the merging of black holes produces signals precisely as relativity predicts, or whether there are hidden deviations. So far, Einstein's equations have held, even in the most violent collisions. Yet, the tests are young. With instruments like LISA, pulsar timing arrays, and sharper imaging from the Event Horizon Telescope, physicists hope to probe horizons with unprecedented precision. What makes this trial remarkable is that it is not only physics at stake, but philosophy. Relativity describes a smooth, continuous universe where space-time curves elegantly under matter's weight. But quantum theory suggests a granular cosmos, restless with fluctuations, where no continuum can survive at the smallest scales. Black holes expose the contradiction mercilessly. The smoothness of relativity cannot coexist with the discreteness of quantum mechanics. And so, when physicists test relativity against black holes, they are not simply checking a theory. They are asking whether the universe itself is smooth or discrete, continuous or pixelated. They are asking whether space-time is geometry or information. If cracks appear, they will not undo Einstein's work, but reveal the deeper framework in which his equations are only approximations. Black holes are not violations, they are the cross-examiners of physics, pressing its laws until the mask slips, demanding a more complete account of reality. In their darkness, the trial continues. With every merger, every photon, every shadow casting its silent testimony. At the very heart of the paradox lies a scale so small that human imagination recoils, the Planck scale, where distances shrink to 10,3,510 circumflex, -35, 1035 meters, where times are measured in 10,4,410 circumflex, -44, 1044 seconds, and where energies rise beyond anything achievable in stars or colliders. It is here, at the threshold of the Planck regime, that general relativity and quantum mechanics clash most violently. And black holes, by collapsing matter into infinitesimal regions, drag us directly into this forbidden territory. The singularity predicted by relativity is not merely an inconvenience, it is a symptom that the continuum picture of space-time cannot be trusted at such scales. Quantum theory, when pushed to these extremes, demands fluctuations so fierce that the smooth fabric of Einstein's geometry shreds into foam, virtual particles churn in violent seas, space-time warps and twists in frothing instability. This is the trans-Planckian problem. Near the horizon, Hawking's derivation of radiation requires modes of arbitrarily high frequency, energies exceeding the Planck limit, where the very assumptions of relativity collapse. What happens in this storm? Some theories imagine space-time becoming discrete, quantized into finite units of area and volume, a cosmic lattice replacing the illusion of continuity. Loop quantum gravity builds on this idea, suggesting that singularities are avoided because the granular structure of space prevents infinite compression. Instead of infinities, one finds bounces, where collapse halts and reverses, though in ways we can scarcely picture. String theory proposes another resolution, that the fundamental building blocks are not points but vibrating strings, whose finite size naturally softens the infinities. Singularities dissolve into tangled webs of brains, where geometry is replaced by richer structures. The fuzzball proposal arises here, suggesting that what appears as a smooth horizon is in fact a dense quilt of microstates extending outward to the scale of the horizon. Yet all remain conjectures. No experiment can yet probe the Planck scale directly, and black holes conceal their secrets behind horizons. We are left with indirect tests, looking for subtle imprints in Hawking radiation, echoes in gravitational waves, or deviations in the structure of cosmic backgrounds. The philosophical implications are stark. If space-time is not continuous, then our deepest intuitions about length, duration, and smooth motion are approximations, shadows of a reality pixelated at scales far beyond perception. Black holes, by dragging physics into the Planck realm, are reminders that our maps of the cosmos are written in an incomplete language. Do they break physics? Or do they reveal the point where one grammar ends and another begins the seam, where continuity gives way to discreteness, where relativity yields to quantum gravity, and where the universe whispers that even space and time are not eternal truths, but emergent illusions? If the Planck scale remains unreachable in the cosmos, physicists have turned to ingenuity, building laboratories where horizons can be mimicked, if not directly summoned. These are analog black holes, systems in which the mathematics of waves and flows mirror the equations of relativity, allowing us to test in miniature what the universe hides in vastness. One such stage is the flow of fluids. In the 1980 seconds, William Unruh proposed that sound waves in a moving fluid could behave like light near a horizon. If a fluid flows faster than the speed of sound within it, then acoustic waves cannot escape upstream. A sonic horizon forms, a perfect analogue of the gravitational event horizon. In this controlled environment, researchers realized one might test the very mechanism behind Hawking radiation. Experiments followed. Water channels Bose-Einstein condensates cooled to near absolute zero, optical fibers carrying pulses of light all became arenas where horizons could be imitated. In these systems, pairs of phonons or photons emerge spontaneously at the analog horizon, just as Hawking predicted for black holes. Some experiments have even reported the faint statistical signatures of Hawking-like radiation, not in distant galaxies, but in tabletop setups, whispers of cosmic principles in laboratory chambers. Though these analogues are not true black holes, they lack gravity, singularities, and the cosmic scale of collapse. They capture the essence of causal boundaries. They show how horizons are not mystical but geometric. Wherever waves are trapped, the same mathematics applies. And if Hawking radiation is seen in analog systems, it strengthens the case that it must also be real in astrophysical ones, though too faint to detect directly. Beyond fluids and light, physicists imagine other testbeds: superconducting circuits, plasma flows, metamaterials, sculpted to bend waves in horizon, like ways. Each experiment is a window, imperfect yet precious, offering clues about processes otherwise hidden for eons. These laboratory horizons do more than confirm equations. They remind us that black holes are not alien entities, but natural consequences of wave dynamics and causality. The abyss is part of a wider language, one that echoes wherever horizons form, whether in the collapse of stars or in the rippling of water under human hands. In these experiments, the paradoxes of information and radiation are distilled into forms we can probe, manipulate, and test. They are small rehearsals for the grand cosmic performance, offering glimpses of how the universe conducts its symphony of geometry, waves, and quantum law. Even if no laboratory can yet mimic the singularity or the vastness of a galactic black hole, these analogues whisper an essential truth. The mysteries of the abyss are not infinitely remote. They touch the world here and now, in water, light, and matter shaped by human curiosity. If black holes radiate, if their horizons shrink, then the story of evaporation demands an ending. But what does that ending look like? The question cuts deep into both physics and philosophy, because the fate of a black hole is also the fate of information, energy, and the very rules of the cosmos. For stellar mass black holes, evaporation is imperceptibly slow. Their lifetimes exceed the age of the universe by orders of magnitude. Supermassive black holes will endure even longer, their horizons vast reservoirs of entropy. Yet time itself is patient. Given enough eons, trillions upon trillions of years, Hawking radiation would gnaw away even the largest giants. What remains when the last horizon dissolves? One possibility is a final explosion. As a black hole shrinks, its temperature rises, its radiation intensifying. In the final instance, it may unleash a burst of high-energy particles, a cosmic flare marking its death. Such explosions have been sought in the gamma-ray sky, their absence setting limits on the population of tiny primordial black holes. Another vision imagines remnants, stable objects left behind once the black hole reaches Planck mass. These relics, too small to radiate further, could store the information once thought lost, preserving unitarity in a silent archive. But remnants raise questions of their own. Why should evaporation halt precisely there? Could they proliferate infinitely, carrying implications that strain the fabric of quantum field theory? A third perspective suggests graceful fade-outs. In holographic models and island calculations, the information flows out through radiation, leaving nothing mysterious behind. The black hole ends as it began, an arrangement of quantum fields, dissolved into the wider universe. No fireworks, no relics, only a smooth return of what was once hidden. Philosophically, each scenario carries weight. Explosions mean that the end of darkness is an act of violence. a final flare in a cooling cosmos. Remnants suggest permanence, tiny seeds of information outlasting galaxies and stars. Fade-outs whisper of cycles, of conservation without spectacle, of a universe that tidies its ledgers without drama. What unites them is uncertainty. Our theories cannot yet decide. Observations are mute, for the timescales are beyond reach. The answers lie in the interplay of gravity and quantum law, at scales where neither alone can guide us. In contemplating evaporation, we glimpse the end of all stories. For if the universe lasts long enough, black holes will be the final actors on the cosmic stage. Long after stars have died and galaxies have dissolved, their slow fading will mark the last whispers of activity in a darkening cosmos. Their deaths will not merely end themselves, they will close the curtain on creation. Amid the paradoxes, evaporations, and singularities, there is another truth about black holes that is quieter, but just as profound. They are not merely destroyers, they are also engines of balance, regulators of cosmic order. Far from being isolated anomalies, black holes shape the evolution of galaxies, influence the birth of stars, and sculpt the very architecture of the universe. At the centers of galaxies, supermassive black holes anchor their hosts. Their gravity binds stellar orbits, but their influence is not only gravitational. Through accretion disks and jets, they release energy on scales that dwarf entire galaxies. These outflows can heat surrounding gas, preventing it from collapsing into new stars, or compress it, igniting starbursts. In this way, black holes act as thermostats, regulating the life cycle of galaxies. Without them, galaxies might grow bloated with stars or stagnate in silence. With them, balance is maintained, growth sculpted into order. Astronomers see this influence in correlations. The mass of a galaxy's central black hole is tightly linked to the velocity of its stars, the so-called m-sigma relation. Though the black hole is only a fraction of the galaxy's total mass, its presence dictates galactic structure. This is not coincidence, but a feedback loop. As the black hole feeds, it shapes the galaxy, and as the galaxy evolves, it fuels the black hole. Together, they form a partnership written into cosmic history. Even on larger scales, black holes leave fingerprints. Their jets can extend for millions of light-years, heating intergalactic gas, influencing the formation of clusters and redistributing matter across cosmic webs. In simulations, when black holes are excluded, galaxies grow too fast and too large, diverging from what we see. It is the dark engines at their hearts that enforce the universe's patterns. On smaller scales, stellar black holes recycle matter. When a massive star collapses, its death spreads heavy elements into space, iron, carbon, oxygen materials essential for planets and life. Black holes, by consuming stars and merging, help spread and stir these elements, enriching galaxies with the raw material of existence. Seen in this light, black holes are not mistakes or failures of physics. They are participants in creation. Their gravity forges order out of chaos. Their violence fuels renewal. Their presence ensures the cosmos does not collapse into disorder or drift into lifelessness. Perhaps the greatest irony is that what we fear as absolute erasure is also a force of continuity. Black holes regulate the cosmos, not by breaking physics, but by ensuring its balance is kept. They are not only questions about the edge of law, they are part of the law itself, written in energy, entropy, and time. In their silence, they shape the music of galaxies. In their hunger, they give the universe rhythm. They are not only ends, but engines. At the edge of every horizon, there is a silence that is not absence, but presence. A pause in which the universe seems to whisper its most secret grammar. Black holes, those engines of collapse and paradox, have forced us to ask whether the laws we hold sacred are permanent or only temporary scaffolds destined to be surpassed. Do they break physics? In one sense, yes. They summon infinities, contradictions, and puzzles that no theory has yet resolved. They show us where relativity and quantum mechanics cannot coexist, where determinism fails, where the map of space-time dissolves. They are the test sites of our ignorance, the places where the language of physics stammers. And yet, perhaps they do not break physics at all. Perhaps they are physics at its most honest, revealing its incompleteness not as defeat but as invitation. The singularity is not the end of understanding but the signpost toward quantum gravity. The paradox of information is not destruction but transformation, the reshaping of law into something richer. Horizons are not walls but pages, inscribed with information in ways we are only beginning to read. For humanity, black holes are mirrors. They reflect our hunger to know, our fear of forgetting, our struggle to reconcile the infinite with the finite. In their darkness, we see both the fragility of our theories and the resilience of our questions. They remind us that science is not about final answers but about reaching the frontier where knowledge meets mystery and listening to the silence beyond. Perhaps the greatest lesson of black holes is humility. They are not exceptions to the universe, they are the universe, distilled into extremes. They are not mistakes in the fabric of law, but the places where law reveals its deeper weave. Whether they break physics or rewrite it, they are the horizon toward which thought must fall endlessly until new truths emerge. And as we contemplate them, the abyss does not stare back in menace, but in patience. It waits, as stars wait, as galaxies wait, for us to learn its language. And now, the fire of paradox softens into an ember. The collisions, the jets, the screams of torn stars all fade into the background hum of the cosmos. What remains is the quiet rhythm of time stretching across eons. The black holes, those vast engines of gravity, linger in silence, their horizons dissolving in radiance so faint it will never touch human eyes. The universe itself grows still. Stars burn out, galaxies dim, and only the black holes remain, like coals glowing at the end of a fire. One by one, they too fade, evaporating in whispers of radiation, releasing the last measure of information back into the cosmos. It is not a violent end, but a slow, patient exhalation. A universe once filled with light and motion settles into calm, the drama of creation and destruction giving way to something gentler. The abyss, once feared as a destroyer, reveals itself as a keeper of balance, a custodian of order. Even in death, it obeys the deeper harmony of law. For us, who dream beneath the stars, the lesson is quiet but enduring. Mystery is not failure, it is the shadow of knowledge yet to come. Black holes do not threaten meaning, they deepen it. They remind us that even in darkness, the universe carries a story, written in horizons and echoes, in entropy and light. So rest, knowing that physics is not broken, only unfinished. The night is vast, the questions unending, but the search continues. And in that search lies the truest music of the cosmos, the calm certainty that there is always more to learn, always more to see, always more to wonder. The stars fade, the horizons wait. Sleep now, under their silent watch. Sweet dreams.